Hello guys, welcome to our second part of chapter 17 about reliability and maintenance. So this part actually is the calculation part and so on. So this calculation is mainly going to be based on the network about reliability. Now in this case, I'll show you how do we solve a system that is a network like the one that we already have here. And then yeah, this is what we'll do for this part, and the other part will be about maintenance. Now in this case here, as I'm going to do with you, whenever you have a map like this or a schematic like this, the first thing that you need to do is to think of it like a map, in the way that, you know, when you have a map, they tell you you always start somewhere and you always finish somewhere. So you cannot, let's say for example, you want to go to 10, you cannot go to 10 by skipping 1 2 and then you just fall on 8. Normally you need to go like a normal guy, 1 2 3 4 4 5, 3 4 5 and so on and so on. Now same thing apply in this case here. We have a map and we need to be able to interpret what the map is saying and where you need to start and where you are going. Now in this case here, first of all, they say that below are schematic of your organization process A and B. So we have two processes already, A and B, and then they say that consider that the process are in series, which means we have A that is in series with B. So this one is another information, and according to our information, this is process A, this is how it look like, and this is process B. So we need to find the reliability of process A, then we'll work it in series with the reliability of process B. And then one thing that you need to know to solve these formulas here, you just need to know the formulas that I showed you in the previous video about what to use if we are in series, if we are in parallel, or we have a redundant. Now in this case here, you will identify that the system is in series when they are following one another. It is in parallel when we have one on top of the other, and it is in a backup when we have the main component with a little component that is just down below. Now in this case here, let's start with process A. Now from the information that you have here, we identify already that we have RS1, it means reliability of system 1. We have RS2, reliability of system 2, RS3, and so on and so on. So we need to follow all these numbers step by step. By the time we get to the last one, and we will find RSA, which is the reliability of system A or process A between bracket. Now first thing first that we need to do is to identify our system. We have RS1, and according to what we have right now, RS1 is a system has two components, and these are our two components. Sorry, we have no field. Let me highlight it in red like this. So RS1 has two components, and these two components here is 0.91 and 0.92. Now these two components, they are in series because they are following one another. So what we do, we calculate for RS1. So we have RS1, it has two components, and according to our calculation, the two components are 0.91 and 0.92. So actually this one is process A. So we have RS1. RS1 has two components, 0.91 and 0.92. Why am I multiplying? Because it's part of our formula. Whenever you have component in series, as we did in the previous video, you take the reliability of the first component times the reliability of the second one. Now in this case, we have 0.91 times 0.92. 91 is the first component that we already have here, and 92 is the second. And then based on this, when you calculate the formula, the answer that you get is 0.8372. I want to emphasize on the thing that in this case we are talking about a reliability, and we say that reliability was the probability. A probability is either in percentage or actually is in percentage, but in this case here we divide by 100, so we don't need to put any unit, we keep it like 0.83. This is RS1, we just solve it. Now we go back to our map, we just solve RS1. But now if you look, I'm going to erase this part here. But now if you look at the map, you'll notice that we have RS2 here. But now RS2 is not the component that is down here. RS2 is this whole thing here. And then based on what we did, what we need to do is like errors2 now involve errors1, the part that is up here, and the 0.95 here. So this is errors2. So that means errors2 is, first of all, I'm going to put it like two components. The first component is the one that is on the line errors1, and the second is the one that is down, which is 0.95. And according to our formulas that I showed in the previous video, again, for us to calculate errors2, because they are in parallel, so we will have 1 minus, you open your bracket, 1 minus the reliability of errors1 times the 0.95. Why 0.95? Because actually is times 1 minus 0.95, and I close the bracket for the second time. Actually, this is the part of the formula, so you need to look at the previous video to understand the formula, but this is how it applies. And in this case here, the value of errors1 is already given, we found it, which is 0.8372. Now based on our, as I said, as I recall, so we have errors2 is made of two components, errors1 and errors2. Errors1 we already found it, errors2 is here. Now based on that, if you replace the formula, of errors1, you will notice that errors2 will give you a value of 0.9919. So now 9911, remember that the errors1 here has a value of 0.83. So this is, you replace it here and you put your formula into your calculator. As a matter of fact, on this part here, we are going to work with 4 decimal places. I repeat it again, we work with 4 decimal places to get the most accurate number. We don't limit ourselves to 2, we will keep 4 decimal places. Now we just found errors2 here, then we need to look for errors3. Now based on the map, error3 is here, and then wait. So now error3 is this part here, and error3 is only one component, I mean two components, but we have the main component, the 0.75, which is now the main component because it is on this line here, but it also has what we call, how can I say, it also has a backup. Now sorry, what am I saying? error3 is this all part here, this is error3. Yeah, errors3 is this all part that involve the first component with 0.75 with a backup of 0.95, then we have errors2, and then we have the 0.95. So how do I know that that is what errors3? Because on this line we only have errors1, errors2, that is this, which means error3 obviously will be this whole line here. So now we need to put our all formula. First of all, we have error3. We need to put it step by step. error3 is, between brackets, we can call it like 4 component, I mean 3, first, second, third. So this is the first component here, 0.75 with a backup of 0.95. Now which means according to our formula, we will get the probability of the first component to work. The first component is the main one, 0.75, plus the probability of the second component to work, 0.95, that you multiply by the probability of the first component to fail. And in our case here, the first component is 0.75. So if its probability to work is 0.75, so its probability to fail will be 1 minus 0.75. So in this case we have 1 minus 0.75, and then we got the first part here, and whatever you wrote is only this part. But remember that it is, this part is in series with errors1 that we already have here, I mean errors2 that we already have here. So here we have the value that we have times errors2. Why did I multiply it? Because as I said, we are working in a system that has 3 components in series, the first, the second, and the third. The third is 0.95, so that means here we multiply again by 0.95, and the value of errors2, we just got it here, the 0.99. So if we need to replace it here, the value that we are supposed to expect is going to be 0, because whatever we are working now is error 3 is 0,9305. So now this is the value of error 3. How do I find these values here? You just put this all formula into your calculator. By the way, do not write S2, so S2 replaced by its value that is here. Then we got error 3, so we need to work for error 4. Now we look at our map. Where is error 4? Because we are going somewhere. According to the map that we have here, error 4 is this. It's only S2 component, because this is where error 4 is, and these two components are in series, 0,96, 0,97. Then I go back to my table here. Error 4 is two components, 0,96 times 0,97, and the answer that I'm supposed to get is 0,93102, and this is my answer for error 4, and that's it. Why? Because as I said again, this is just a reminder. This is the middle part, and so on, and it has two components, 96 and 97. Remember that this blue square limitates, it tells me where I'm working. Now in this case I got errors 4. Where is errors 5? Errors 5 is just down here, which means that errors 5 involve this whole square. So errors 5, this is our errors 5 between bracket. So this is my value of errors 5. It has three components, the first, the second, and the third. And the first is 0,852, which is in parallel with 0,96 and 97, which are made by errors 4. And then we have the last one, 0,91. And then write the same formula, but in my case here, what I'm working on is a system that is in series, I mean parallel. So the formula is 1 minus, I open my bracket, it's the same formula that we use for errors 2. I open my bracket, which gives me 1 minus, in this case it's 852, 1 minus 0,852, close it, times, in my case I look at the middle part is errors 4, so here I have errors 4, times the last part here is 0,91, and then I got 0,91 here. And then based on the information that I get, those are the components, but I need to remove the 1 here, so it will be, open my bracket, 1 minus errors 4, and here I do the same thing, which is 1 minus 0,91, like this, and then I close the bracket and I get my value. Now the value of errors 5 is supposed to be 0,9991 after calculation. Again, as a reminder, we are working with this thing with 4 decimal places. So we just work errors 5. Now we need to work for error 6. Error 6, we see that it is this line here. We see that it involves now this component and this component here. This is our value of error 6. Now how many components does it have? It has 3. So we have the first component, 0,92. We have the second component, which is error 5 that we just worked out, and then we have 0,99. So what we do, we repeat the same formula, but in this case error 6 has components that are in series. So what we have 0,92 that we multiply by errors 5, that we multiply by 0,99, and the value that we're supposed to get for error 6 gives us 0,91. In short, you are going to get 0,9099 something, but by the time you round it, you are going to get a value of 0,91. So let me repeat for error 6. Error 6 is here, is this whole line here. But now remember that what delimitate at now is this whole square, which means error 6 is here. It comprises 3 components, 0,92, errors 5, and 0,99. This is what we just did with our formula again, and the components are in series, that's why we just multiply. Then we need to work out for error 7. We done with error 6. Error 7 is the part that is just down based on our calculation. Now based on our map, this is error 7. error 7 is the part that is down here, and it is 5 component: 0.95, 0.79, 0.98, 0.75, 0.99. But you notice that the second and the fourth component have backups, which is 0.95 and 0.95. We'll also include them in our formula, but you know that this part here is 5 component, all of them are in series. So that means error 7 will give us a value of 0.95 first. The 0.95 is this first part, plus, times, we open our bracket, 0.79 plus 0.79 is the main component, its probability to work, plus its probability, or the probability of using the second, 0.95, times the probability of the first component to fail, which is 1 minus 0.79. Actually, it's not the first, it's the main component to fail, like this. Then we just put this one and this one. We need to include this one in our formula, 0.98 time. We do the same principle like the one we did here. So you have 0.75 and 0.95. Now the main component is 0.75 plus 0.95, which is the backup, times the probability of the first or the main component to fail is 0.75, like this. Then we need to multiply by the last value of 0.99. Remember, as I said again, now we have 4 components, 5, all of them are in series. We have the first, the second, the third, the fourth, and the fifth. Now in this case here, we are working for error 7, which should give us a value of 0.9006. So this is how you solve about error 7. Now if we go back to our map, like from here, you notice that we have 0.95. This one is the backup. By the way, this part is excluded, the 0.91. I want you to be confused. Yeah, so we have 0.95, 0.79, and so on. This is the part. So we just solved error 7, but we need to find error 8. And according to our map, you notice that error 8 is this. Actually, is this all square here. So if we need to put it, we can put error 8 to be like this. But then, if you look at our map, it is made up of 3 components. We have the first one that is just up here, which is R3. We have the second, which is just in the middle, which is R6. And you have the last one that is just here, which is R7. Now, which shows you that whatever we have here is 3 components that are in parallel. So R3, 6, and 7. Even from here, you can see them. That means we look at our map, we go back here. You're working for errors 8. The formula is 1 minus, I open, 1 minus error 3 times 1 minus error 6 times 1 minus errors 7, I think. So the value, we take them from here again. We have error 3, error 6, and error 7, and the values are from here. So we have error 3, 6, and 7, and they are in parallel. That justifies the use of this formula here. And then from here, errors 8 gives us a value of 0.9994, and then we got our value of errors 4. Now errors 8. Now we need to look for errors 9. Now based on the map that we have here, errors 9 is just little, cute, and simple. This is our value of errors 9. Sorry, the value of errors 9 is just this one here. It only involves 3 components that are already in parallel, and the formula is almost the same as the one that we use for errors 8. So now in our case, we have 1 minus, you open your bracket, 1 minus the first component, which is 0.73, times the second component, which is 1 minus 0.98, times the last component again, which is the same reliability as the second, 0.98. So it's 1 minus 0.98, and the value that we get is supposed to be 0.9999. So we have 4 nines. So this is the reliability of system 9. And then we need now to find the reliability, the last one, because there's no RS10, there's only RS9, and then we have RSA, which means reliability of system A. Now based on what we have here, you notice that the system has 3 components. We have the first one, which is RS9, the second, which is whatever we just worked out here for RS8, like this, and we also have that little component that we just have on the side, which is this. I don't want to confuse you guys, but I hope you'll find. So you see that RS8, RSA has 3 components: the big one RS8, RS9, and the last one here, and all of them, you see that they are in series, they are following one another. So the formula is easy in this case. We have the reliability of system A, that is equal to RS8, that is in series with RS9, that is in series now with one component with a backup, 0.88 and 0.97. So in our case, we get the reliability of the main component 0.88 plus 0.97, the reliability of the second component or the backup times the reliability of needing the second or the probability of the first one to fail, which is 0.88. Again, like a tip that I always give in class, I always tell you, the value that you get here will always be the same as the value that you minus here. In many of our exercises, whenever you have a backup, it's always like that. Same applies in this part here. We have 0.75, 0.75, 0.79, 0, this is just a tip or a clue for you to help you find your way. Now we said that to find the reliability of system A, we have RS8 times RS9 times this component here with it backup, and the main component 0.88 and 0.97. So we have 0.88, 0.97, and we have our formula. Again, I'm not replacing these values here because we know that we already get them from here. So that means RSA gives us a value of 0.9957. So now this is the reliability of the system A that we're looking for. This system that we just solved here, this is the reliability of its system. This is the reliability of this system. But remember that we have 2. We have A and B, which is different. Now we just solve A. Now we need to solve for process B. This is process B. Again, the principle is still the same, in the way that we are working with a map. You need to know where is RS1, RS2, RS3, where are we going, and life will be more easy. Now in this case, if we didn't catch for process A, let's start over for process B. Process B, we have RS1, which is this, and it's only 3 components, 0.91, 0.97, 0.65. all of them are in series, in parallel. So what we're solving now, we just solve process A. So that means we need to solve process B. Process B here. So we need to solve by RS1. RS1, 3 components, all of them in parallel, as I said, 0.91, 75, 65. So formula is the same. 1 minus, you open your bracket, 1 minus the reliability of the first component, which is 0.91, the one that we have here. 1 minus 0.91 times 1 minus the reliability of the second one, which is 0.75, times the reliability of the last one, 1 minus 0.65, I think. Yeah, 65. Then This is how you solve RS1. And in this case, the answer that you get is 0.9921. Then you find with RS1. Then you go to RS2. RS2, the principle is strictly the same. Component, we have 3 components, so we have these ones here. We have 3 components, 0.90, 0.82, 0.77, and this one also are in series, in parallel. So what you do, you have 1 minus, you open your bracket, 1 minus 0, in this case is 0.90, which is the first component, times, you open your bracket, 1 minus, and then in this case we have 0.82, we close, times this one, the last one, which is 0.77. So it's 1 minus 0.77. Then from here we got our formula, and the answer that we get is 0.9959. So I'm rounding off again as I repeat. I'm rounding everything to 4 decimal places, and also you must make sure that you put this whole formula and you round out the final answer. You can put part by part depending on cases that I'll show you, or like in cases like where we did with this part here. I think this one where we introduce everything into the calculator, but it's okay. So just put the whole formula into your calculator, and the only thing that will be left to do is just round out the final answer. Now we need to solve RS3 based on our map. RS3 is here. Same principle, 3 component, 0.878172. So this one is RS3. How many components? 3. So the first component is 1 minus 0.87, I think. And then the second is 0.81 times 1 minus 0.81 times 0.72. 1 minus 0.72. Now the value that we get for RS3 is supposed to be 0.9931. Then in this case we have RS1, RS2, RS3, and then everything is on our map here. And yeah, we have 1, 2, 3. But I want you to notice something, that we have an RS4 here, and the RS4 is this line, which means we have 3 components that are on it, which is RS1, 2, and 3. So these 3 components here are part of RS4, and all of them are in series, which makes our life here, we just need to times them. So we have RS4, that is RS1 times RS2 times R3. Now in this case, the formula that you get, the answer that you get is 0.9812. Now we just take these values here, you multiply them, and you get your value. This is how it works, because they are in series. Then in this case we're done with RS4. Then we need to come back and we try to solve again. After 4 we have 5, which means we need to go to RS5, and this is RS5 according to our map. This is RS5 because RS5 is down here and the line is like this. Now that means it's a 3 component in series, 945, 92, 99. So we have RS5, which has 3 components, 0.945 times 0.92 times 0.99. Now this is the value that this is how we find for RS5, and the value that we get is 0.8607. Yeah, 0.8607. This is for RS5. Then we do the same thing for RS6. I think the principle is the same, the system, but this one is the one that is down here. So you have 92, 985, and 91. Now in this case here, reliability for RS6 with 0.92 times 0.985 0.985 times, here you have 0.91. Now in this case also the answer that you get is 0.8246. Again, as I'm saying, you must be able to round your answers correctly. Now error 6 make it 0.8246. Now as I said, the principle is still the same. You just need to be able to identify which part is it and so on, and you find. Now in this case here we just did error 6, error 7 is here. Obviously it means that since it's on this line, it means that it involves errors 5 and error 6. So error 7 is the sum of all these two here. But these two, you notice that they are in parallel, errors 5 and error 6. We already found the value of errors 5, already found the value of error 6, which makes our life easy. We have error 7, which is because they are in parallel, 1 minus, I open my bracket, 1 minus errors 5 times 1 minus error 6, like this. We already get the value of errors 5, 0.8607, error 6, 0.8246. Then from here we replace everything in our formula, and the answer that we get is 0.9756. Now this is the value of error 7. Just replace them in the formula. As I said, you copy and paste the value in the calculator. Actually, there's no way to copy and paste, but you repeat them the way you just write them. Now we just did error 7, which means we need to go to error 8. But something interesting, error 8 is here. And based on error 8 is made of two components, errors 4 and errors 8. So if we should highlight, the more important part of this should be like this. This is errors 8. It involves only two components. It doesn't involve the one that is done, so it's only this one, which is errors 7 and errors 8. And the two, remember that they're in parallel. So that means we have errors 8, and the formula is 1 minus, you open your bracket, 1 minus errors 4, close your bracket, times 1 minus errors 7, I think, like that. So we have errors 4 and errors 7, and all of them are in series. I mean, they are in parallel. So this is the formula that we use, and then you replace the values. The value of errors 8 that we found is 0.9995. So this is how you find errors 7. I mean errors 8, and the values, as I said, they are already here. We use for errors 4 and errors 7. Then from here we go to errors 9. What is errors 9 telling us? This is errors 9. Errors 9 only has 3 components, and these 3 components that we have based on our, so these are our 3 components. Actually it's 4 components, with the first component that has 2 components in backups. In backup, I mean, we have errors 9, which has 0.65, 0.74, 0.95, and the 0.99, which is a backup to 0.65. So we write down our formula. We get our 0.65 plus 0.65 plus 0.99 times 1 minus 0.65. Again, why do we use this formula? Because this formula is used for backup, and this is the backup. How do we know that the backup? Refer to the previous video. I explain everything easily. This is the main line. It shows you that the main component, and the one that is here is the backup. We will use it only when the one of 0.65 doesn't work. And the formula is 0.65 plus 0.99 times 1 minus 0.65. You get your answer, times the value that you get here. I mean, it's 0.74 and 0.95 because they are in series. So 0.74 times 0.95. 74 and 95. Yeah. Now from here, the value that you get is 0.7005. Now we find with errors 9. Now we need to find the reliability of system B. As I said, there's no errors 10, which means that even if we need to solve, errors 9 is the last one and we'll stop from there. But you notice that after errors B, which is the reliability of system B, has two components, errors 9 and errors 8. And errors 8 based on our map here is all this thing. Yeah, all this thing. So we notice that errors 8 has two components. The reliability of system B has two components. Errors 8, which is on top, and errors 9, which is down here. Now we already get the reliability of errors 8, the reliability of errors 9, which means it's easy. It's just a normal reliability, the normal parallel thing. 1 minus, you open your bracket, 1 minus errors, which errors is it? Reliability of system 8 times 1 minus the reliability of system 9, like this. And that's it. The reliability of system 8 is already found here, system 9 is already found here, and after replacing the value, the reliability of system B is 0.9999, like this, and you find with this. But then remember that actually we're not done yet, because this one is the reliability of system B. But now we need to find the reliability of this process, because these people, according to what they say that below are the schematic of your organization's process. So the organization process, between bracket, includes A and B in series. We just found process A, process B. So what we should do is like reliability of the whole system. So the reliability of the whole system is going to be the reliability of system A times the reliability of system B. Why am I timing them? Because according to whatever they told me here, they say that the system is in series. They could have said it in parallel, and we could have used something different, another formula for if they were in parallel, but in this case they're in series, and based on our final answer we get 0.9957 times 0.9999, and the value that we get is 0.9956. Now this is the final answer to this model here, and this is how we get it. So by now I think you guys must be fine about the reliability and the system. I think our next video will be more about maintenance and so on, and that will be the last part about this chapter. Thank you so much for your time, and I really hope that this video will help you, and yeah, you enjoy. See you for the next video. Thanks.